The definition of a plane that we're going to use looks very similar to the definition of a line. We're going to put the definitions side by side to show the similarities and talk a little bit about mathematical language before taking a deeper look at planes themselves. A line in space is the set of terminal points of vectors emanating from a given point P that are parallel to a fixed vector V. A plane in space is the set of terminal points of vectors emanating from a given point P0 that are perpendicular to a fixed vector n. As you get further along in math, definitions become more and more important as the foundation of how you think about things. It's very important that our definitions are as precise as possible so that the rest of our ideas can also be as precise as possible. When you think about definitions in this way, you can start to get a sense of the flow of the language, which not only helps you to think about definitions, but also theorems and proofs. The first line is stating the name of the object being defined. The second line describes the type of object that is being defined. In this case, it's a set of terminal points of vectors. The remainder is a set of descriptive phrases that describe the property of the object being defined. What do we know about these vectors? They emanate from some point and have some relationship with another vector. Understanding this framework will help you organize the information in your head to make it easier to remember and less prone to error. And that can be very helpful in being successful in a math course. But at this specific moment, it's probably not of central importance that you make this connection. As you keep studying math, you will find that it's useful to slow down and make sure you're starting to catch some of these higher level patterns in how we do math, as it will help you understand what's happening at a deeper level. But for now, we'll return to thinking about the definition of a plane. Definition: a plane P in space is the set of all terminal points of vectors emanating from a given point P0 perpendicular to a fixed vector n. Let's start with the point P0 and draw the vector n emanating from it. Technically, n can be anywhere, but the picture is simplest to visualize if we draw it this way. Let's think about all the other vectors that emanate from P0 that are perpendicular to n and plot their terminal points. For example, there are a bunch of points in this direction. And we can actually think about this as an entire line of points. We can then imagine rotating this line around the vector n to get another line in a slightly different direction. In fact, we can keep on rotating this all the way around, and as we do this, you can see that a plane is being created. To get from the picture to the formula, we're going to use the fact that the dot product of two vectors is 0 when those vectors are orthogonal to each other. We are given the vector n, which we will write as ABC, and we need to get the vector that points from P0 to some point P on this plane. We will call the coordinate of P0 x0, y0, z0, and a generic point P on the plane xyz. Remember, to get the vector from one point to another, we need to subtract the coordinates. So the vector P0 to P is x minus x naught, y minus y naught, z minus z naught. We then substitute and take the dot product, which gives us an equation of the plane. We call this final version the scalar equation of the plane, and we call the original vector form the vector equation of the plane. This is similar to the parametric form of a line and the vector form of a line in that they are both representations of the same thing. The conversion backwards from the scalar equation is a bit more complex this time, but if you remind yourself that it's a dot product, you should be able to learn to recognize it. Just as we often need to find the equation of a line, we're going to need to find the equation of a plane. And similar to finding the equation of a line, to get the equation of a plane, you need two pieces of information: a point on the plane and a normal vector to the plane. There are lots of different ways to get those two pieces, but those are the two pieces you need to be looking for. A common example of this is determining the equation of a plane that passes through three non-collinear points. What's interesting about this problem is just how many different ways you can do it. All you need is a point on the plane and the normal vector. You start off with 3 points on the plane, and it doesn't matter which one you pick because they're all on the plane. So just pick one and move on to the normal vector. How can we get a normal vector to the plane? By taking the cross product of any two vectors that lie on that plane. This is because the cross product of two vectors is orthogonal to both of the vectors you started with. With these 3 points, you can make 6 different vectors that lie in the plane: PQ, PR, QP, QR, RP, and RQ. And as long as you pick 2 that aren't parallel to each other, you can take the cross product to get a normal vector. Once you make these calculations, you just plug it into the formula. The book has an exercise where you do this, and you should take the time to go through it. This section was relatively short and conceptually simple. However, we're going to come back to these basic skills of finding lines and planes often in this course, so you want to take the time to really understand the ideas that we've discussed.